Let's look at ZA mapping for vector axis. We looked at how the tile gets mapped to the ZA array. Now we'll look at how the vector axis is mapped to the ZA array. Here is a ZA mapping of vectors. SVL by 8 rows of SVL by 8 bytes. That is the size SVL B into SVL B would be the size of the ZA array. So for a 128-bit implementation, we have 16 rows of 16 bytes in each row, and ZA0 will give us access to this particular ZA vector array. ZA5 will give us access to this particular ZA vector array. ZA7 will give us access to the 8th row in the ZA array storage. Now that is for a byte access. Depending upon the element size, now the number of columns will change. Let's look at element-wise vector access. Here for byte access, 2 will be accessing this particular row in the ZA storage. I think we looked at vector access in greater detail earlier, so I'll just this again. We wanted to show the difference of byte access and half-word access for a element size of 16-bit. Here 2 of these cells will occupy one 16-bit element, and we'll have only 7 columns, and ZAH, the H suffix, dot H suffix will represent that we are accessing 16-bit element, and 4 indicates the row that we are going to access in the ZA storage. That will give us access to 8 16-bit elements. Similarly, we can use 32-bit access, for which your ZA, instead of H, it will become S. Here is an example of S6. .S6 will access particularly 32-bit element size. So the number of elements in that row would be only 4. Similarly, we can have access to 64-bit element size, 128-bit element size, in which case for a SVL 128-bit implementation, the complete row will have only one element, and that can be accessed as ZA.Q. If you want to access the 0th row, we can access ZA.Q0. For 10, it will access this. For 0, it will access this particular row. Here is a mapping of tiles for a SVL implementation of 128 bits. A .S indicates that you are accessing 32-bit data elements, in which case for a 16 bytes by 16 bytes SVL 128-bit implementation, we'll have 4 tiles: ZA0, ZA1, ZA2, and ZA3. How do we access it? The ZA0 H.B2, the B indicates that we are accessing a byte of the element. And here you want to access the complete ZA0, that is the tile 0. And since it is for 8-bit access, the complete ZA storage forms one tile, that is ZA0. And what we are accessing is horizontal slice of the tile. The ZA0H represents that you are accessing the horizontal tile slice. If we need to access them as ZA array of vector, we'll be using ZA2. That also will give us access to. Here is an representation of how a 16-bit element can be accessed as a horizontal tile slice in ZA0 tile. As the element size has changed for 16-bit element size, the same 128-bit implementation will now have 2 tiles. These rows will form, the one I'm striking in the red will form tile 0. The alternate rows forms the tile 0, starting from 0, and the ZA1, ZA3, they all form tile 1. ZA1 represents tile 1. This is what is indicating tile 1, and the horizontal slice axis is indicated by this H, that is ZA1 suffixed with H. ZA1H indicates tile 1 horizontal tile axis. Dot H indicates we are accessing 2 bytes of the data, or half word of it. Thereby we have only 8 elements starting from element 0. What happens if we access the same implementation of ZA storage as 32-bit element? So here is for the byte access, here is the details for 16-bit element access. Let's see for 4 bytes, that is 32-bit element size. For 32-bit element size, we will have 4 tiles, ZA0, ZA1, ZA2, ZA3. The second row of ZA0 tile will be ZA0 H dot S1. The second row of ZA2 tile would be this. As you can see, the same ZA array vector can be accessed as ZA6. It can be accessed as ZA0 H dot B6. You can access it as ZA0 H dot H3. You can access it as ZA2 H dot S. That is, when you're accessing it with 16-bit element size, you will be part of 0 tile. When you access it as 32-bit element size, it will be part of ZA2 tile. So SME provides greater flexibility to access the vector of elements depending upon how you want to sort out the data within the ZA storage. Say you want to sort it out as 4 tiles, then use a 32-bit access. Thereby, you can have 4 different matrix simultaneously living in the ZA storage. You can use the SVE2 instructions, you can use the SME instructions to manipulate these data, that is, process this data and store back the result within the ZA storage, and later on move the results onto the memory as well. That is using the store instruction. Or if you want to load it, you can use similarly all these representations to access a particular array of data, right? This is for quad, 128-bit access, 32-bit access, 32-bit access. This is for 64-bit. This is for 32-bit. Similarly, this is for 128-bit access. Okay, that's about the horizontal tile slices mapping. Let's have a look at how the vertical slice mapping looks like. The ZA0 represents tile 0, and we are accessing the vertical slice. That's what the V represented in orange color indicates, and we are accessing a byte-sized element. Dot B represents that, and 2 indicates the row which we are accessing. There is a example implementation for 128-bit implementation. We have 16 by 16 rows and columns, and for vertical access, we'll be using ZA0 V for the slice. There is only one tile. What if we access the same ZA storage for 32-bit element size or 16-bit element size? For 16-bit element size, we'll be using, for 16-bit element size, we'll be using 2 cells for holding one 16-bit element. Each square is 8-bit, whereas the number of rows remains constant. So for vertical slice, since we are using 16-bit, we will have 2 tiles mapped to the ZA storage, tile 0 and tile 1. And this particular row that we are accessing will be part of tile 1. That is what ZA1 indicates. Since it is a vertical slice axis, it is represented by V, and the dot H represents 16-bit element axis. The 2 is the number which you are accessing. That is the column that you are accessing. So within the tile 1, that will be ZA1V dot H2. Note that when we have the horizontal axes, when we form the tile, the alternate horizontals form the tile 0. Similarly, when you are accessing the vertical slice from tile 1, not all of these elements will be accessed. The tile 1 will have only 7 of the elements. So those 8 of the elements. So those 8 would be element 0. 1, 2, 3, 4, 5, 6, 7. Since we counted from 0, it is 7. So those elements will form the vertical slice, as this row will be part of ZA 0 tile. That's what is shown here, ZA 0 tile. And here we are accessing tile 1 vertical slice. So the blue ones, the elements colored in blue, would be the elements that we will be accessing as part of tile 1. So the complete blue cells forms a 16-bit element. This is what would be accessing. This will be element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8. That is these 2 blue cells put together. Those will be forming the vertical slice. right? Similarly, for mapping for 32-bit element is shown here. Since the explanation is same, I would not go through details again. All the required details have been detailed on the slide itself. Just that we'll have 4 tiles here, ZA0, ZA1, ZA2, ZA3. And since we are accessing 32-bit element, the access size, the .s suffix is used. And since we are accessing a vertical slice in ZA0 tile, we start from this. This becomes an element of ZA0 tile, a slice S2. All the blue cells constitute one element in that slice. And similarly, 1, 2, 3, 4. 4 elements will be there in that particular slice for a 32-bit access. Similarly, for 64-bit access, there'll be only 2 elements. That's what is. And for 128-bit access, there'll be a single 128-bit element. All right, that's about the ZA storage. How we can access the ZA storage as vector access, tile access, and vertical slices and horizontal slices within the tile.